Yeah, that's good.
Right.
Okay, so let's go. So now you can go to the. Yeah, sure. Check, check, 1, 2, 3. Test, test, 1, 2. Check, check, 1, 2, 3. Test, test, 1, 2. Check, check. Are you able to hear yet? Test, test, 1, 2, 3. Check, check, 1, 2. Is it like really loud? Okay, so we can turn it down on the Zoom.
It's just like a delay.
Yeah.
That's all.
Yeah. So I think we're able to.
This is pretty.
Is it like okay, or do you think we should like turn down a level? Test, test, 1, 2. Check, check.
Oh, I like it. You're gonna turn maybe just like a little bit. It's not bad. Yeah.
Let's do that quickly. Oh, does this? Oh no, original sound kind of mess with things. Am I struggling? Yeah, pretty low. Did I not press? Did I not press send? Oh, I think I was. Yeah, there we go. Oh, it's an outreach social media. Yeah, sorry. Check, check, 1, 2. Test, test. Is the live stream working? James will try to figure that out in about 10 seconds. Cool.
I think this is fine. They can turn down the volume if they want to. This is perfectly fine.
Hi, everyone. We're going to start in a couple minutes. I just want to direct you to the check-in right here, just to let us know that you've signed in. You will be entered into a raffle to win some Columbia Astronomy merch if you are signed in. So just a little bit more incentive to sign up. But we'll get started in a couple minutes. Let people trickle in. All right. Are you on the live stream? Okay. Check, check, 1, 2, test, test, 1, 2, check, check, 1, 2.
That were the third one just for fun.
Yeah.
So which will know whether it works or not. I mean, why don't we start like this, and then if it interferes, I'll take it off and put it there. See. Hello.
Yeah.
Hello, 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 hello. Should I like
Maybe
put on the, yeah. Hello? Is that better? Check, check, hello? Hello?
project.
Hello, can you hear me?
Yeah.
Sounds like it. Yeah,
Awesome.
cool,
So you could like put on your.
cool. Yeah. Should I turn it off or?
Yeah, we'll turn it off. So, like you could wear that. We'll turn it off.
Okay, just got this.
Maybe.
Just put it on the tripod, my phone. Can I just use your phone? Yeah, my storage is out. Or I can ask one of my family. Cool. Max's. My phone didn't have enough storage. If I get up there and it's not pointing at me, feel free to move it the right way. Yeah, could you actually just hold a ring light for me? I didn't. Probably fine. I could grab another phone if you're worried or if you need battery afterwards. All right. Are we doing trivia first? Yeah. I'm not doing trivia first. All right. All right, cool. Actually, I didn't get the clicker going. How do I do that? I don't know how to check if my clicker is
working.
yeah, because the slides are like off screen.
Oh.
I don't know how to find them because they're like somewhere over here. I guess I can do it when I come up here.
Yeah.
And if clicker's not working, I can just abort.
I think
Should just track. Okay, whatever.
doesn't work.
I think also, can you turn that on as well?
I don't think so.
Okay, yeah, just remember to switch on.
Do I need to do anything to get it to read, or should it just automatically know that there's a clicker there and it works?
You put the-
I put the USB in the USB. Okay, cool. So just turn it on and then, okay, cool.
我在大学上课是吧？
Hopefully I don't disappoint.
All right. Hello, hello. Check. Oh, it's muted. It's muted. Hello, hello. All right. Thanks for coming. We're going to get started. Yeah, welcome to Astronomy Night. These are our semi-weekly public lectures and observing nights. My name's Justin. I haven't done this before. I haven't emceed, but fingers crossed that this goes well. But yeah, I'll redirect you again. If you haven't signed in, please do so. You will be entered into a raffle during the Q&A after our talk for some Columbia Astronomy merch. If you're interested in that, please do sign in with that tiny URL or that QR code. So, yeah, public astronomy night. Woo! Okay, I did not expect that voice crack. Yeah. Okay, so our program tonight, we'll have some trivia led by me, and we'll have talk by one of our grad students here, Daniel Yahalomi, and afterwards you can ask him all about his research. And depending on the weather, we may or may not be stargazing tonight out on College Walk. So I'll announce that formally after the talk, after we make sure that skies are all clear. And yeah, that's the layout. And yeah, let's get started with some exoplanet trivia. So I'll show you the questions and just a show of hands after I announce all the answer choices. Sounds good. Question 1. While only 8 planets orbit our sun, a myriad more planets or exoplanets orbit stars far beyond our solar system. As of April 12th, 2024, how many exoplanets have we confirmed the existence of? Is it A, 577, B, 5,602, C, 12,066, or D, 102,356? I'll give you a little bit of time to just mull that over. All right, show of hands for A. B. Okay, C. Okay, and D. So the correct answer is 5,602 B. And unfortunately, you don't get a prize if you get all of them correct. So this is just brownie points. Yeah, so question 2. Arguably, the first definitive discovery of exoplanets occurred in 1992 when Puerto Rico's Arecibo Observatory detected 2 planets orbiting the object PSR 125712. What type of object is PSR 125712? A compact neutron star, B, a star similar to our sun, C, a red giant star, or D, a gas giant slightly smaller than Jupiter? All right, show of hands for A, compact neutron star. Cool. B, a star similar to our sun. C, a red giant star. D, a gas giant slightly smaller than Jupiter. I actually forget the answer, so let me just fast forward. A compact neutron star. Awesome. Congrats if you got it. Question 3. Many techniques have been developed to detect distant exoplanets. Which of the following is not a viable exoplanet detection method? Is it A, looking for eclipses of distant stars as seen from Earth? B, measuring minute wobbles and the motions of stars? C, thermal imaging of the space around stars? Or D, landing small space probes on rocky objects nearby distant stars? All right, who thinks it is choice A, looking for eclipses of distant stars as seen from Earth? Cool. B, measuring minute wobbles and the motions of stars? Okay. C, thermal imaging of the space around stars? Or D, landing small space probes on rocky objects nearby distant objects? Cool. Cool. So, oh, it is D, landing small space probes on rocky objects nearby distant stars. Awesome. All right. We're 80% there, almost. Yeah. Question 4. Many exoplanets have been discovered using the transit method, or the detection of eclipsing planets moving past the face of a star, resulting in a dip of the observed brightness of that star. What information can we not glean from observing a transit with this method? A, the radius of the transiting planet. B, the composition of the exoplanet's atmosphere. C, the orbital period of the planet. Or D, the distance from the planet to its host star. Oh, Mike died. Awesome. I'll change microphones to right here. Okay, who thinks it is choice A? Choice B? Okay. Choice C? Or choice D? All right, I saw some exoplanet astronomers not even raise their hands, so they're not even sure of this question. It is the composition of the exoplanet's atmosphere. And question 5. So far, 3 exoplanets have been detected via astrometry, or the detection of wobbles and the motions of stars. The upcoming Nancy Grace Roman telescope promises to detect even more exoplanets with its astrometric accuracy of 10 microarc seconds or less. With this accuracy, what is the smallest object that Roman could detect on Earth from the location of the moon? Is it A, size of an ant, B, a ping pong ball, C, a basketball, or D, a typical car? All right, show of hands for A, an ant. Okay. B, a ping pong ball. C, basketball. Or D, a typical car. All right, if you guessed choice B, you are correct. Thank you for playing trivia. I guess I will have to awkwardly do this all night because the wireless microphone has died. So yeah, let's get to announcements. So our spring program is almost wrapping up. Today we have Daniel giving his talk. April 26th, we have Ryan potentially giving a talk. He's the typical MC for this evening. I'm filling in. We're switching roles. And over the summer, you might expect to see programming from us. It depends on our capacity to, put out such events. But stay tuned on our socials. We'll be posting all about it, and also we'll be emailing about it. So stay tuned for that. Yeah, so Astronomers Without Borders is collecting solar glasses. Hopefully you observed that eclipse on Monday. I know everybody around me has been talking about it. Hopefully you got a chance to observe it, maybe from New York or upstate New York or somewhere across the US. Yeah, so if you have any solar glasses that you'd like to recycle, you can bring them to the next lecture. So the Astronomers Without Borders is collecting solar glasses and giving it to those who need it for other eclipses in the future. So yeah, so if you have solar glasses, you can bring them after the talk up here. And if not, you can always bring them next time. All right, and without further ado, we're going to have Daniel Yahalomi give his talk from Wobbles to Worlds, developing a framework for detecting the unseen. I guess I will read his bio right now. All right. Daniel Yahalomi is a fourth-year PhD student in the Department of Astronomy and Astrophysics at Columbia. His research focuses on the architecture and dynamics of multiplanetary systems, particularly from an observational and data science perspective. With a background in physics from MIT, he worked at Harvard as part of the TESS science team and as a volunteer and co-director of the Harvard Science Mentoring Research Program for high school students. He is a AAS National Osterbrock Fellow, an LSST Data Science Fellow, and a NASA Exo Explorer. Outside of astronomy, he is a skilled athlete, from hiking and backpacking around the world to running marathons and regularly biking to Columbia from downtown Manhattan. Be sure to ask him about his water polo accolades after the talk. And yeah, without further ado, I'll introduce Daniel.
Moment of truth. Oh, I see. Can I get it on here? So I don't know how to get it full screen. It's not mirrored. Sorry, give me a second. Okay. Let's test this. Cool. All right. Yeah. Hi, everyone. Daniel Yahalomi, as was said. Can you hear me in the back? Great. Okay, so first of all, I'll just say I'm like really excited to be here and to get to talk to you all. I remember being like an elementary school student and coming to one of these talks, and yeah, it was really a special moment for me. So it feels kind of full circle to be back here and get to talk about some of the stuff we're working on. Now it's only my name on the slide. My advisor is David Kipping. I've worked with, I've had the, luck of working with a lot of amazing mentors and other colleagues. A lot of them are sitting here, but so more people than I can think. But it's like in astronomy always. It's not just me. It's a lot of other people, which is one of my favorite things about the field. Is it's a really big team effort. So with that, I'll get started. I'm going to be talking today about from wobbles to worlds, how we can develop a framework to detect the unseen. And as some of you astute viewers might have already noticed, I've started with a picture of the total solar eclipse from this past week. I was really excited when I realized I was talking, several days after, because the core of my research is really just looking for these same eclipses, but around stars rather that aren't our sun. So here's a nice image of the total solar from this week. Here's one from 2017, a composite of a series of 7 photos of the partial eclipse and the total solar eclipse. And so I'll start with just a simple question of why do solar eclipses happen? Why do we see these total solar eclipses on Earth? It's really just a geometric happenstance. So these aren't to scale, but their relative sizes are good enough to get the derived effect. So we take the Earth, the Moon, and the Sun, and we trace out what their angular diameter is in the sky. you find that they have approximately the same angular diameter. And what that means is when the moon passes in front of the sun, even though it's much smaller physically, the relative distance of the two objects means that the moon can block out essentially the entire sun. And this is a consequence of the fact that the distances between the Earth to the moon, which is about 380,000 miles, and the Earth to the sun, which is about 150 million, sorry, this is kilometers, 150 million kilometers, has the same ratio approximately to the diameter of the two objects. So they're both approximately ratios of 400. And so when you have that effect, that means they have the same angular diameter. It's about 0.5 degrees in the sky. That's why they block each other. You can also see this if you ever like looked at a full moon, and you shouldn't look at the sun, but if you have a sense of what the relative size of the sun is, they're about the same. So they have the same approximate angular diameter. In our solar system, it turns out this is the only moon and planet system that we know that has this geometric occurrence. So for example, we could look at the Mars-Phobos system. And if we look at that system, the moon has a smaller angular diameter from Mars. And what's really cool is thanks to instruments like Perseverance. This is a real image of Perseverance rover. I think it was taken in 2017. No, it was later, 2020 or something. So the big rover is Perseverance, and the little guy in the background is the Ingenuity helicopter, which recently went offline. But this is actual footage from Mars. And what in a couple years back, the Perseverance rover was able to capture an eclipse of Phobos passing in front of the sun. And you'll see here that even though it's passing right through the middle, or approximately the middle, it only blocks out a small portion of the light. So if you've ever seen a partial eclipse, it's not that the moon passes fully in front of the sun, it's that it passes on an angle. Whereas here, the relative angular sizes aren't the same, so you get only a partial blockage. Okay, so this is eclipses. I'm going to be talking today about transits. So typically when we talk about eclipses, we're talking about moons passing in front of the host star from a planet. When we're talking about transits, we're talking about a planet passing in front of its host star as viewed from another planet. And so here is approximately what you'd expect for a Venus transit in front of the sun. And in fact, we can observe that as well. So this is an image from one of NASA's solar telescopes. And this is a real transit of Venus, which are the black dots passing in front of the sun as viewed from a telescope that's orbiting the Earth in a low Earth orbit. Okay, so that's transits. Now what's an exoplanet transit? Now we're going at a completely different scale. So now instead of objects in our own solar system, we're talking about stars, other stars in our Milky Way galaxy. And so I've done up this stretching, and you can see that we're blocking much, much less light. In fact, what we find, and so now I've flipped the angle, and now we're looking at a planet passing in front of its star, like face on. And we'll see these three stages of the orbit. And if we observe the brightness of the star over time during the orbit, we find on the right that when the planet passes in front of its host star, it blocks a portion of the amount of light. And so these are called exoplanet transits. And I'll just go back again to click through that. The idea being, so you're looking at the light received from the star. In this first section, the planet isn't blocking any of the light, so the relative brightness is constant. In this portion, the planet passes in front of the star, and so you block a certain percentage of the light. And then again, for this portion of the orbit, we're not blocking any of the light, so it's flat again. And so these are these transits, exoplanet transits that you might have heard about, or that has, as Justin has said, have been very successful at finding exoplanets. So the transit method has been used to find many known planets. To date in total, astronomers have discovered, confirmed about 5,600 planets. I think it's 5,602. I can't see my slide. And of that, I think about 4,000 of them are using transits, like 4,200 have been found with transits. So the vast majority of the planets we know about have been discovered via the transit method. We can see that also on this diagram, which shows the number of planet detections by method year to year. And you'll see that there are two real workhorses in this exoplanet transit game. One is the Kepler Space Telescope, which launched in 2009, and one is TESS. So Kepler launched 2009, operated for 9 years, went offline in 2018, and then TESS launched in 2018. So Kepler observed over 500,000 stars. It discovered, to date, 2,779 planets with an additional about 2,000 candidates, but it only observed about 0.25% of the sky. So what Kepler did is it observed a very specific field for 5 years, that one location of the night sky with a 1-meter telescope was able to observe relatively deeply and find both bright stars and faint stars, kind of everything in that field. TESS took a very different approach. So TESS is basically just 4 CCDs essentially in space. There's no big like telescope lens, but because you're in space, you don't have the atmospheric contamination, so you can still observe the brightest and most nearby stars. And so TESS has observed around 200,000 stars. It's confirmed around 432 stars, but there's an additional 7,000 or so exoplanet candidates. But it's observed around 93% of our night sky. And how it does it is with these tiled sectors. So you're looking at a schematic of how TESS observes the night sky. Each of these rectangular sectors is observed for 27 days. And so what it does is it tiles the southern hemisphere for about 1 year, and then it flips and it tiles the northern hemisphere. So it launched in 2018. It's now on its, had a primary mission of 2 years. It got extended. It's now on its second extended mission, and hopefully will be operational for years to come. And here's a comparison of TESS versus the Kepler field. So that main field in the top left, in yellow, that's what Kepler observed for the first 5 years. 5 years in, 2 of the reaction wheels on the telescopes failed, and so we weren't able to hold stable on that one location in the night sky. And so what the engineering team was able to do, which is pretty spectacular, is figure out that they could stabilize it enough to point for short periods of time at the ecliptic. So that's why it observed this area in the middle. And this diagram is only good for the first 2 years of TESS. That's why it doesn't look like it covered 93% of the night sky. It's now kind of filled in some of that, more of that space. Okay, so one of the major results of the Kepler Space Telescope, which you might have heard been advertised and discussed, is that there are more planets and stars in the Milky Way. And so with those stats that I gave you, this might be surprising because Kepler observed 2,700 planets after observing 500,000 stars. And I'll just tell you, there's about 100 billion stars in our Milky Way. So how can we claim that there are more planets and stars when we only have seen 2,000 out of an observed 500,000 in 100 billion stars in our Milky Way? And so we have to understand not only our, the strengths of the transit method, but also the drawbacks of it. And so I'll say there's 3 main ones. The first is there's a low probability of planets being properly aligned to transit. So for an Earth-like planet around a Sun-like star, the probability of transiting is 0.5%. What this means is if we're looking at a Sun-like star and we know there's a Earth around it in our neighborhood, just geometrically, if you look, it only transits if it passes in front of it like this. If the orbit is at all inclined, it won't transit relative from our viewing angle, for our vantage point. And the geometry, the geometry, let me know if you can't hear me. Yeah, the geometry, the spacing between successive, or between the objects means that for most of these orbits wouldn't actually pass the star. And in general, the further the planet is, the less likely it is to transit. So what that means is that even though we've only discovered 2,000, it is likely that we have more planets orbiting stars. Statistics to extrapolate out what are the other planets consistent based on additionally, oh yeah, it's just harder to detect smaller. So the bigger the planet is, the more light it blocks from the star. And so a fundamental property of
transit observed telescopes is at the minimum detectable transit depth, which equates to the minimum detectable size. The last thing is that there are multiple true astrophysical signals that can mimic transit signals. So a lot of effort has been put into kind of statistical differentiation between what's a true positive and false positive transit. Okay, so I suggested that in many cases, planet could be orbiting a star, but it's geometrically not transit by the transit method, never find it. So, and I said that in many cases, a planet or a moon is too small where our telescope isn't sensitive enough to detect it. So how might we hope to find objects in the stars? And so what we could do is look for these wobbles. And so I'll run this through a couple times. But the idea here is if we see a planet transiting, and there's a moon orbiting that planet, its orbit won't be a perfect circle. Instead, the moon and the planet will orbit each other as they orbit the sun. And so if you look at what our transit looks like, you'll find that successive transits will be early or late based on the effect of interacting. So in our diagram here, in purple would be what would be the expected transit of this planet with this moon around it. You can see that I put like how here is the transit time if there's no moon around the planet. How PTB is this observed. Additionally, though, you get a similar effect if you have two planets orbiting the star, and the interaction between the planets create a similar effect. So you don't get the really quick effect that you then observe a longer alias effect, but you observe that the planet's interaction with itself leads to the same wobble effect. So again, here's the green planet, the green planet, here's the blue planet, it's interacting with that green planet and try to distinguish it by that version. However, in practice, we don't see the image on the left. All we see is these transit times on the right. And I purposely made it such that there's the reduced transit variation is the same for the planet because oftentimes that's what we observe. So all we can see is the variation. But what our data set might look like over a series of 5 years over time is you see that the planet is sometimes early, sometimes late. And so these wobbles in the orbit of the planet is used by other physical objects consistent with transit time effect. And I'll say that it makes it difficult without knowing what's causing it while we don't see both objects in the system differentiate. Okay, so that's kind of the whole ramp-up preface. Now I'll get into what my work is on. So my project is how can we try to go from these wobbles to these TTVs that I've spoken about to these worlds, so either detecting moons or planets. And I'm going to do it via 2 routes, either the exomoon corridor or the exoplanet. So hopefully up to today you have a little sense of what are these paths from all these worlds and how we're kind of treating together. Okay, so I'm going to show you some real data now. Brace yourself. There's a lot of time and effort that went into these. You don't understand what the time I questions afterwards. I spent years looking at these, so yeah, be warned. Okay, so what you're looking at here is 2,600 systems from Kepler Space Telescope. They're all transiting planets. Each black dot is a transiting planet. What I've plotted here, though, is that about 1,900 of them that favor TTV signal over no TTV. So essentially, we did is we fit a periodic signal to the observed transit times, and then we fit a model with no variation. And then we ask the question, which is statistically favored, and in about 75% of the time, it favors TCP. So it seems like variations are very abundant in our data set. And if we're just thinking about, the solar system that we know the best, itself, we know the best, there are 8 planets, most planets have moved, a lot of objects interacting, so it's probably not surprising that these aren't perfectly consistent. I'll also note that, as I said before, a lot of these on the x-axis here is the orbital period, which means what is a year for this planet. So the Earth will live in 5 days on the x-axis. And then the y-axis is the amplitude of the TCP signal minutes. And I'll just put here where the amplitude of Ganymede, which is the orbit of Jupiter, and our moon would live. And I'll also add here Kepler 1625 BI, which is a exoplanet candidate that was identified by previous grad students at Columbia, Alex Tichy, and David. Okay, so I promised 2 effects. Let's get into the first one, the exomoon corridor. The idea around the exomoon corridor is that we observe planetary transits once every transit, by definition. You're going to get 1 data point every year for that planet. But the period of the wobbles of a moon planet system, the true period, will be equal to the period of the moon, right? The moon is orbiting the planet, it's invoking a periodic signal. That's the true period. But we sample it on a period that's equal to the period. The transient planet, by definition, is always going to be longer than the period of the moon. So we'll always observe the alias. When I say alias, it sounds like a big scary math word. It's something you see every day. If you're driving down the highway and you look out your window and you see a car moving, car tire moving really quickly, the rotation rate of the wheel is faster than the frame rate of our eyes. And so we can't see the true motion, the true period of the tire's motion if you're in the alias, if you're a longer period. That's what's happening there. So it's the same effect with moon data. So simulated here is how that happens. So in gray is what a true TCP signal would look like for a moon orbiting the planet. In black is where we would observe the observations. And you can see I can fit a sinusoid model to that data set. You get the next curve, right? The alias period, which is longer than the true period of the signal. And I'll just skip a lot of math and derivation. I'm happy to talk about it as much as you want after this. But in 2020, data skipping showed that a consequence of these aliases is that 50% of moon TCPs would live between 2 to 4 times the period of the moon. So it uses these fast TCP periods that equal to 2 to 4 times the period of the transit planet. What's interesting about that is if you plot that on the diagram, what it shows in white is the simulated alias exomoons, and in yellow are known planet-planet TCP systems. You'll see that not only do moons oftentimes induce TCP in a short period of time, but planets don't very often induce in this exomoon corridor. So there's only a contamination rate around 1%. About 1% of the known planet-planet TCPs fall into this fast period. This is a good place to look for possible new moons. That's exactly what we did. This is again the same data set that I showed you before.
Hello? Can people hear me? Zoom? Hello? Yeah. Okay. But now I'm showing just a downsampling that we did. And so we applied a series of 6 cuts to the data, selecting for more moon-like signals, doing things like removing systems that we knew to have multiple planets in the system, moving systems that had amplitudes that were too large to be caused by a TTV of the moon, so on and so forth. When we do that, we end up with 11 targets, but really one system stood out. and it's called Kepler 1513b. We're not really good at naming planets in astronomy. It's just like a convention, but it is what it is. So Kepler 1513b is a gas giant, so it's like a Jupiter or Saturn-like planet at 160 days. So it orbits its star once every 160 days. And now that we identify the system, we wanted to answer the question, is this unseen companion to this planet a moon or another planet? And so here's the real data of the transits. And the bottom in purple is the Kepler data set. You can see the strength of this 1 meter telescope in space. There is actually a black model fit through that data, but it like looks perfect. And then about 10 years later, we observed 2 more transits. So in green and blue, we observed the same transit. And then in orange and red, we observed a transit 2 orbits later. And what I've done here is we just stack them on top of each other, folding by the period. And so you could see where they all line up. And what I've plotted here is the TTVs. So what you're doing is those wobbles that I showed you before, you find the variation in the midpoint, and that's what I'm plotting on the y-axis. So you can see that in the Kepler data set alone, this is just the Kepler data, that we have this short period signal. That's a period about 2.6 times the period of the transiting planet. However, when we added in these 2 additional observations, we find that the short period signal persists, but there's an additional long-term period. And so this long-term period is not conducive to having a moon, and is also very, is what you expect from a planet-planet system. And so with this, we knew that that's no moon. And we identified Kepler 1513c, which is most likely a Saturn mass planet with a close to a 5-to-1 resonance, which means its orbit is about 5 times longer than Kepler 1513b. I'll just say that there's more systems that are still exciting in this exomoon corridor. There's one in particular, Kepler or KOI 3762. And there's an additional transit in June we're hoping to get from the ground and try to reproduce these results and see if we can learn if there's another planet, if there's a moon, what's causing these TTVs in the system. Okay. Quick pause. Exomoon corridor, we're good. We know how to get from Wobbles to world through the exomoon corridor. Now we're going to get into the exoplanet edge. Okay, so the exoplanet edge is the fact, and I'm going to tell you the answer now, and then I'm going to try to walk you through it, but I'm going to be a little hand-wavy in the derivation, that a planet will never induce a TTV with a period faster than half its own orbital period. I'll say it again. You have 2 planets in a system. They're orbiting the same star. The outer planet will never induce a TTV with a period that's faster than half its own orbital period. Why is this? So we have to remember that we observe, again, transits only once per transit of the transiting planet. I'm saying transit a lot. In this case, we're talking about the green planet as the transiting planet, and the blue planet will be this exterior perturber. And what I'll do is I'll walk you through what these TTVs will look like, and I'll freeze it every time this green planet transits. And so what you see is that even though there's a faster true period, again, we're getting the same aliasing effect that we saw for moon-induced TTVs when you have a distant perturbing planet. And when I get here, I'll be able to say, so for this case, for the first half of the external planet's motion, you find that when the green planet is transiting, the other planet is ahead of it during its transit, and so it's pulling it through. When it's pulling it through, it causes an early transit, and when it's lagging on the second half, it's pulling it back, and so it's causing a late transit. And so we find that this alias, by definition, will be equal to the period of this exterior planet. Now, there's another effect that has half this orbital period. I'm not going to bother you with the math. Again, if you want to talk about it, I'm more than happy to. But I'll just say that there exists another effect that creates the same aliasing effect with 1/2 the period. And so this induces this exoplanet edge with a minimum observable period equal to 1/2 the period of this external perturber. Okay, so we can reproduce a similar thing that we did in the exomoon corridor. We go back to our Kepler data, and we found that 22 planets, so now we're looking at 2-planet systems, and we're trying to see if any 2-planet systems induce a TTV that looks faster than is explainable, that's faster than this exoplanet edge. And we find 22 of them that do. So what could cause these? Perhaps there's another planet in the system. We know 2 of the planets are transiting, but you could pack a 3rd planet in between the 2 planets, make it a little bit inclined so it doesn't transit, so we don't detect it, and maybe that could cause it. Maybe it's a moon. Maybe it's a highly eccentric planet. So those are the 3 options, but either way, it means that there's something more in this data set. There's more to discover, and we think it's a really exciting other path forward. Okay, so we're almost there. I'll just put up some takeaways and I'll take any questions. So the first takeaway is transit method has been very successful. It's found 4,000 or so planets, which is a lot. But in the context of thinking that there are more planets and stars in our Milky Way, you could also say it's not a lot. It's not anywhere near 100 billion. And so if we want to really get the most out of our data sets, we have to develop tools to try to study and search for these hidden planets. I say that, and then I'm trying to do that. So we're developing some of these tools. We're hopeful that we'll be able to build computationally efficient ways to look through these full transit data sets. Our current best bets are these searches of the exomoon corridor and the exoplanet edge, which hopefully start to craft out sections of this orbital landscape, and then we can look further and try to analyze these systems on a population level. So I'll put my roadmap back up. I'll take any questions.
So, I guess, maybe this is something I'm not understanding. I noticed a lot of the examples they mentioned were more sort of Jupiter, Saturn, planets. So I guess what I was wondering is, in terms of the technology that we have, I guess sort of how far are we from being able to detect, more Earth mass, like what do we call it?
Yeah.
Some distance kind of planets.
Yeah. So with
yeah,
for sure. Yeah. So I'll say that I think I'll say 2 things. First, it's easier to find bigger things. So it's easier to find larger planets. It's also easier for most of our current detection methods to find things that are closer to their host star. So we've gotten a lot of hot Jupiters, warm Jupiters, meaning Jupiters on like 10-day, 20-day, 50-day orbits, or Saturn's gas giants. We have also found terrestrial planets, so Earth-ish, Earth-size rocky planets. We found more of them around smaller stars because it's always about the relative size. So there are stars like they're called M dwarfs, which are significantly smaller than our sun, and so it's easier to find terrestrial or smaller gaseous planets around these M dwarfs. About the Goldilocks zone, we have found, astronomers have found some exoplanets that are in a region where liquid water could exist. For the most part, they're around these smaller stars as well, because the smaller stars also emit less heat, and so you can be closer to them and still be in the Goldilocks zone. So like TRAPPIST-1 is a famous one, but those planets have like order 10-day orbits. But some of them are in the liquid water zone.
Okay.
And then looking forward, sorry, Justin mentioned Roman because he said that. This Roman telescope will launch in a couple years. It'll be using this method called microlensing. which will actually really help our ability to detect planets that are further from the host star. Difficulty with microlensing is you only get a single observation and then it's gone. So you get like a single pulse and you can't follow it up at all. But if you find it, it can help our understanding of demographics. And yeah, we're pushing towards, I mean, the next JWST currently is called the Habitable Worlds Observatory because we want to be able to directly image Earth-like planets around sun-like stars. So that's the goal in the next, couple decades.
Okay. Whoop, testing. Okay, before we take any questions, let me just direct you to, if you're too shy to ask Daniel a question, we have this tiny URL form. It should pop up on the screen. Yeah. Feel free to ask anonymously. I'll have it pulled up over here, and I'll be monitoring that. But yeah, we'll continue taking questions.
Yeah, there are some people who look for single transits. For the most part, when you're doing transits, you're looking for multiple observations. So with the stuff we're doing, it's yeah, I wouldn't think there'd be anything like that. But you can actually use these same data sets to look for distant comets, asteroids, stuff in our solar system. And if you want to hear more about that, you should talk to Ben, who's right there, and is doing a really cool project looking for stuff in our solar system with test data. I don't know off the top of my head. I don't want to make something up. Yeah, I think another takeaway statistically from the Kepler mission. I don't want to. I'll get back to you. Yeah, I'll look it up and get back to you. Yes, Dad. Yeah, I promise I didn't plant him, but that was a very good question for the research I'm doing. No, but basically what happened is, so I'm framing this issue with TTV analysis with the analysis of these wobbles, as you have this degeneracy between planet-moon systems and planet-planet systems. It has not really been solved. If you go back to 10 years ago when Kepler launched and suddenly we had this wealth of transit data, there was a similar issue. And that issue was, how do we know that this dip we see is actually a transit and it's not these other false positives? The common false positives for transit signals are eclipsing binaries, which mean two stars orbiting each other, stellar activity. So stars themselves vary. You can have star spots that look like a planet transit. And basically what astronomers were able to do is develop statistical techniques that allowed them to study the Kepler candidate planets on like a large scale. There's a single paper, Tim Morton published it in, I guess it was 2017. I thought it was 2016. But there's a single paper confirmed, I think like 1,400 exoplanets. He still like the most planets anyone has found, and it was a single paper because he wrote this package that you could like pass all the data through and then you just got planets. So the dream is basically try to build something similar for TTV analysis. Yeah, the question is about inference tools. A lot. I kind of stumbled into this more theory-heavy project, but there's a lot of like observational data that's motivating a lot of the stuff that we're finding. So how the process tends to work is we have like these data sets and we try to analyze data sets and look for where are interesting cases. And then once we find these interesting cases, then we follow them up, and then following them up shows stuff that we're confused about. And then we try to look deeper into those things we're confused about. In practice, I'm not sure exactly what you mean by inference tools, but a lot of this is coding.
Yeah, I haven't used AI in my model. I think there are people who do transit detection with AI. One of the things, the difficulties with TTV data is that the data is quite sparse. Again, you only get one observation per transit. For transit detection itself, there's been a lot of effective work using like AI models. I think language models is the one that's been used, but uh, I've played around with some toy stuff on the TTV data set, trying to like group them together in any way and haven't found anything meaningful. But doesn't mean that it won't happen in the future.
All right. Let's start our raffle. So yeah, I have a random number generator here, and I have all the responses from the sign in. If you want to participate and you haven't signed in, sign in right there, tinyurl.com/astro dash hyphen check dot hyphen in. All right, let's see. We'll be raffling off the pencil first. All right, 103. Who is lucky number 103? Is Chloe Jones here? All right, come on down and get your pencil. No problem. No problem. We'll continue on with questions and we'll do this all throughout the night. We'll keep going and going. But more questions for Daniel, please.
Yeah, in the back. Yeah, so we can definitely request more. It tends to be ground-based. So like how we were able to disentangle the moon planet signal in the Kepler 1513b case is that we identified this target and then we asked for ground-based observations from collaborators. So a group in San Diego, a group in, I think, the Canaries, and then a third group observed two different transits. And then we were just lucky that TESS, which is the current space telescope, happened to observe a sector when it was transiting as well. So that's one thing. We can do follow-up observations. You also kind of have to get fortunate because Kepler was so sensitive to faint stars that it means that a lot of the stars it observed are not easily detectable from the ground. They're like too faint to get accurate measurements from the ground. I will also say, so right now I'm working mostly with Kepler data. That's just because it's the one where transit time catalog exists. TESS is now observed for multiple years, these continuous viewing zones at the southern and the northern poles. And I'm sure there's a lot of TTV data there. So there's going to be more data that exists. In 10 years, another thing that Roman will do is it'll give us like 100,000 planet candidates because it's going to be observing so many things. So we're going to have this huge wealth of data. And if we don't build tools to study them more efficiently, then we're kind of going to have more to work with and we know what to do.
TTV data be influenced by other detection methods than transit, such as gravitational wobbles? And how would you parse that out?
Yeah. Yeah, so that's a great question. I'll repeat it for people. Zoom, I don't know. Anyway, the question is whether you can use other observational methods with TTVs to learn more about the system. A lot of the most exciting results in exoplanet analysis comes exactly there when you can observe an object with multiple detection methods. Typically, different observational methods observe different things. And additionally, if you can observe it with two independent observations, independent methods, then you're much more confident that it's really there. So with Kepler 1513b, we tried to get some radial velocity observations, which I think what you're mentioning, the wobbling of the star. But the star is really, really active. And so that activity makes it really hard to nail down the motion of the star itself, for example. But yeah, it's a very common thing in exoplanet analyses is if you have a target, you try to observe it with other
method. So if you have a transit, you get the radius. If you from the radial velocity, you can get the mass. From that, you can get the density, so on and so forth. Mm-hmm.
How will the size and abundance of influence data that gather?
How will the size and abundance of moon influence it? So is the question like, what if there's no moons, or what if there's less moons or a lot of moons? How would that, yeah. So I think that's in large part what we're trying to figure out, because well, you can approach it from two ways. I think one of the arguments as to why looking for moons is really interesting is that in our solar system, at least, it's very hard to make planets and not make moons. So at least for the bigger planets, for the gas giants, like they all have many moons. And even like, you know, like Earth has the moon, Mars has 2 moons. Like there's a lot of just other, there's a lot of moons in our solar system. So it's, our current thinking is that when you make planets, you just make moons as well. And so if you don't find moons, once we get to the, you know, detection capabilities where we expect to find them, that might reveal something interesting about our solar system formation being different than others, which we don't expect. So we expect to find them. But again, because we're in this era where we're just now, we just now have telescopes that realistically could observe directly, or not even directly, observe like a transit of a moon. Again, if you want to hear more, you should talk to Ben about his JWST proposal to observe a moon. Outside of that, we're trying to get the most information we can from the data sets we have. And so if we can break these degeneracies and say this signal, that's a real TTV signal, we can show it's real and we can show it's inconsistent with a planet, then that lets us know, at least on a population level, maybe what the demographics of moons look like.
All right, I'm gonna continue raffling off some objects here. Okay, so next up we have a Metro card with an asteroid on it, I think. This is good for one round trip. This is not Columbia merch, not Columbia sponsored. But I've added the stragglers that have signed in late, and generating a random number now. All right, who is lucky number 96? We have Daniel Yahalomi, the father of Daniel. Come get your Metro cards. Not fake. All right, next up we have a Columbia Astronomy magnet showcasing the observatory on the roof of Pupin. All right, let me generate the random number. 73. Who's lucky number 73? Let's see. This is so not planted. This is Benjamin Yahalomi. This is not rigged in any way. This is just such a interesting coincidence. Congratulations.
How do you know that I know him? Yahalom is a very common.
Yeah, that's fair. That's very fair. It could be anybody. But okay, we'll continue taking any more questions. Yeah, sorry.
So the exomoon corridor, the idea behind this was like first realized in 2020, which means we just had more time to study these effects. So right now, the exoplanet edge is just like something that we've realized, we haven't been able to follow up any of these systems and confirm. So I'd say to date, the corridor has been more successful. But yeah, I don't, there's a lot of interesting systems that hopefully the edge will show us as well.
I'm going to butt in with a question from online. Okay, in your view, are there any particularly promising alternatives to the transit method in terms of identifying exoplanet candidates? Or do you expect that this will continue to be the standard even as new technology develops? You sort of alluded to this.
Yeah, no,
Or-
there's going to be a huge amount of planets discovered by other methods. So for the last like decade or so, this European telescope called Gaia has been observing like the full night sky. And what Gaia is doing is looking for what's called astrometry. So astrometry is looking for you basically take snapshots of the night sky and you trace out a star's motion relative to other stars neighboring it. And by analyzing the relative motion of all the stars, you can learn about these tiny, again, wobbles, these tiny wobbles in the star that reveal about planets around those objects. So Gaia promises, the original estimates were that it could identify up to 20,000 planets via astrometry, which would suddenly be the winner. But astrometry is actually like probably the first method that was suggested for exoplanet detection. And there's been a lot of struggle along the way in getting telescopes that are precise enough and then breaking some of the difficulties in what those wobbles come from. And so to date, there's only, I think, 3 planets discovered by astrometry. But that'll be another one. Roman, which is the Nancy Grace Roman Space Telescope, which will launch in like 2026, 2027. It's basically Hubble, if Hubble could look at 100 times more sky at once. So it's the same size mirror as Hubble. It's kind of a crazy story. Basically, some government agency just came to NASA and they were like, hey, we have this telescope quality mirror that's Hubble size and you can have it, but you don't get to ask us why we had it, which means that they definitely had stuff looking down on us. They have stuff like that looking at us now. But forgetting that, we got this incredible mirror that is now going to be used for some really cool science. So Roman will be doing microlensing, find probably tens of thousands of microlensing events. Roman will also find maybe tens to hundreds of thousands of transiting events. LSST is a ground-based facility that's getting first light in the next couple of years, and it will be also getting tens to hundred thousands of exoplanet candidates. So like the number of objects that we will detect is going to boom, which again is further motivation to try to build these like computational efficient ways to rapidly model our data sets.
Does a low TTV mean that it's likely only a single planet? And vice versa, it could be, I mean, you're using the variability of the transit time to figure out whether there's a likelihood of a moon or another planet or both, right? So on the other side, it means it's likely only a single planet around the sun.
Yeah, so in an idealized situation, if like the only thing in the entire universe was a planet and a star, then the transits would be perfectly periodic. So once per year would happen, there'd be no TTVs. In practice, if you like just took everything in the solar system that wasn't the Earth and got rid of it, effectively there'd be 0 TTVs, even though there are other stars and neighboring things. If there's truly a single planet, you'd expect to find no TTVs is the first thing. Getting into what if there's like a moon and a planet or multiple planets and a moon, that's a much trickier question. What we found is that, well, probably too soon to say found, but what we think is that in often cases, you'll find a dominant signal. So even if there are like second order effects from say you have like a moon and a planet, one of them will tend to dominate. And so we're hoping that you can break it on that. But in reality, we have to start somewhere. And so the idea is to start with this simple case of one planet or one other planet or one other moon, and then we can go from there. I'll also just note, because I think it's cool, the moon's TTV, like the moon's gravitational effect on the Earth means that every year there's a 2.5 minute variation. So we should really have like a 2.5 minute leap year every year based on where the orbit of the moon is. If we're trying to be, if you care about precision at 2.5 minutes, then we should be keeping track of that every year.
All right, another question from online. How much are you worried about past planet data, i.e. periods or size of being incorrect due to aliasing caused by moons, planets through TTVs?
So, I mean, I think if we're talking about transits itself, then I don't think I'd be worried at all. And any results that have been published from TTVs have been pretty comprehensively modeled. The one outlier there is, like, as we found with Kepler 1513, if you don't have a sufficient baseline of observation, sometimes a longer term signal is just undetectable. But if that's the case, I tend to expect that the effect would be you may be missing a planet in the system. So there's a core result that is going to come out where basically people had got time with James Webb Space Telescope. They've observed the planet, and it showed it like transited like an hour early. And the only way they can explain is that there's a like fourth planet in the system they didn't previously know about. And the influence of that means that the planet they knew about is probably like 20% less massive than they thought. So stuff like that can happen if you're determining the masses from TTVs, where you like maybe miss an object in the system. You might overestimate the mass. But yeah.
Okay. All right, we'll continue our raffle. I know I'm keeping you guys on your toes here. Okay, so we'll do another Metro card, and then we'll do the big prize, which is this tote bag right here with the Columbia Astronomy logo. All right, so for the Metro card, let us get a random number. 108.
Daniel Yahalomi.
Yeah. 108, we have Esme Bennett. All right. Awesome. All right. And now for the grand prize. Maybe we need a drum roll or something. Oh, this is so exciting. Ooh. I'll do it one more time. 80. Okay. 80 is Jeremy Bogle or Bogle. All right. Congratulations. All right, we'll do a couple more questions if that's okay. Yeah. Are you okay with a couple more questions?
Sure.
All right. Any more questions, or I can field some from online?
Yeah.
Find these tiny, tiny little variations. How do you decide like a wobble is what you're parsing through all of that data from the very beginning?
Yeah, so what we do is, especially when we're looking for moons, moon TTVs are very consistent with a sine wave almost always. And that's because moons tend to be, it's called tidally locked, but they tend to not be very eccentric as a consequence of that. And so because they're not very eccentric, you don't have significant accelerations. And so the variations themselves are quite sinusoidal. And so basically what we do is we just fit a sine wave to the transit times, and then we fit what's called a linear ephemeris, which just means flat line through all the transit times. So we fit them independently, we get our results, and then we compare the chi-squared. If you've taken like a statistics class, what we do is the Bayesian inference criteria. We require it to have a delta BIC greater than 10, which indicates strong preference. But it's basically just a chi-squared comparison and ensuring that the sine wave is strongly favored over the flat line.
All right, we'll take a question from online. What is the use for finding exoplanets?
Yeah, no, that's a great question. I think that if you ask, 50 astronomers, you probably get a number of different results. For me, I think it's a number of things. I think going back to those, like, again, when I was like 10 years old and went to my first astronomy talk and thought this was so cool. Just like looking up in the night sky and like seeing stars and trying to wonder what else could be out there. So I think fundamentally what we're able to do in exoplanet searches is search for these other worlds, search for these other places. As I've done more and more work in exoplanet science, I actually find that I appreciate the Earth more. It's like crazy the amount of things that have to happen for the Earth to be like it is. And I think that the more that we study planets around other stars, the more we can understand our solar system, we can understand its uniqueness, we can understand its place in the larger cosmos. Yeah, I think that for me, that's what does it. On top of also just being mind-boggled, like Kate, that you can do these things with tiny intensity variations and all that.
Cool. Let's do one more question. I'll hit you with an existential one. Unrelated question, but with your astronomy background, do you think there exists life on a planet other than Earth?
So if you asked me 5 years ago or 10 years ago or 15 years ago, I say something along the lines of like, there has to be, which is what most people would say. You just say like, if we think there's more planets and stars in the Milky Way, if we think that the average galaxy also has, hundreds of billions of planets, how could there not statistically be life? I think in part from working with my advisor very closely for the last 5 years. And if you want to see a full argument as to why there may not be any life in the universe, you can look at David Bing's YouTube channel. He has another public lecture on this topic. But basically, the idea is that we really don't know a huge number of the parameters that went into creating life on Earth. So we don't know how long it takes life to form. We don't know once life forms, how long it can survive. We don't know all of these parameters that go into the equation. And so if we want to scientifically hypothesize and follow good practice, we really shouldn't say that we think there is or we think there isn't. But in some ways, I think that's more exciting, because I think if we knew for sure there was life out there, then what's the point in looking? And if we knew for sure there wasn't, then what's the point in looking? And it's in that in between, in that area of not knowing that creates the question.
All right. I say we do one more Metro card, and then we can wrap up. Okay. So, random number generator. I'll do it a couple times. 115. 115 is Anthony Gagliardi. Yeah. All right. Good for one round trip on the New York City subway. All right. Let's thank Daniel once again for his talk. All right. So for stargazing, it looks a little bit uncertain right now. We suggest that you stay here for a little bit. We'll maybe see what things look like at 8:30. We have people on the ground looking at the clouds, and I think it also previously just rained a little bit. So we're still hoping for some clear skies. But also in the meantime, if you have any feedback for this event, we'd really appreciate it. Let me know how I did as hosting. Yeah, but yeah, thanks so much for coming to our talk, and thanks for Daniel.
Yeah, I'll be here if you want to come up. You said it too. I saw some.
Oh, good job. Thanks. I hope I didn't keep it the Q&A too long. No. Thanks.
Hi.
Yeah, I don't know. That have those. Maybe like the Eclipse mini lectures we'll be doing at libraries.
Yeah. Yeah.
Yeah, I think people are like
Oh, yeah, we can see.
very